Welcome back to the lab. Today we are tackling a fundamental enterprise networking challenge, enabling multiple VLANs to communicate through a single router interface. This technique is called router on a stick, and it is essential when you have more VLANs than physical router ports. Instead of buying expensive new hardware or multiple routers, we use subinterfaces and 802.1q trunking to carry all VLAN traffic across one physical link. Think of subinterfaces as virtual interfaces on a single physical port, each one dedicated to a specific VLAN. The 802.1q encapsulation standard adds a VLAN tag to each Ethernet frame, telling the router which subinterface should process it. We will also configure a centralized DHCP server on the router so every PC gets an IP address automatically without manual configuration. By the end of this lab, you will have a fully functional Inter-VLAN routing setup with dynamic IP allocation across 3 separate subnets. Let us get started. We start on our router, setting up router on a stick to handle Inter-VLAN routing across a single physical link. First, we bring up physical interface Gigabit Ethernet 0/0 with no shutdown. This activates the port so it can send and receive traffic. Next, we create our subinterfaces and map them to our VLANs using 802.1q encapsulation. We enter GI0/0.1, run encapsulation.1q2, and assign 192.168.2.1 as the gateway for VLAN 2. The encapsulation command tells the router to accept only tagged frames with VLAN ID 2 on this subinterface. We create GI0/0.2, bind it to encapsulation.1q3, and give it 192.168.3.1 for VLAN 3. Finally, we build subinterface GI0/0.3 with encapsulation.1q9 for our management network, assigning 192.168.9.1. Each subinterface acts as a default gateway for its respective VLAN, and traffic between VLANs must pass through the router. Now, all 3 local subnets have an active default gateway sitting on the router. Moving over to switch 1, we first define our VLAN database. We create VLANs 2, 3, and 9 globally so the switch recognizes and forwards traffic for every subnetwork. Remember, VLANs are essentially separate broadcast domains, so devices in different VLANs cannot communicate without a router. Now we configure trunking. Port Gigabit Ethernet 0/1 connects directly to the router. We set switch port mode trunk and restrict it with switch port trunk allowed VLAN 2,3,9. Trunking allows multiple VLAN traffic to traverse a single link, and the allowed command ensures only our 3 VLANs use this trunk for security and bandwidth efficiency. Port Gigabit Ethernet 0/2 connects downstream to switch 2. We apply the same trunk settings here to ensure all 3 VLAN tags carry across the inter-switch link. Lastly, we assign access ports Fast Ethernet 0/1 through 0/3 to VLAN 2 for our first group of PCs. Access ports carry traffic for only one VLAN, simplifying the host connection. On switch 2, we repeat the VLAN creation step, adding VLANs 2, 3, and 9 to its database. Remember, if a VLAN isn't in the global database, the switch drops those tagged frames on trunk links. This is a common troubleshooting point, so always verify your VLANs exist on every switch in your topology. Next, we configure interface Gigabit Ethernet 0/1 as our uplink trunk back to switch 1, permitting VLANs 2, 3, and 9. This trunk carries all inter-VLAN traffic between switches, allowing devices on switch 2 to reach the router for gateway services. Then we assign the local access ports. Fast Ethernet 0/1 through 0/3 go into VLAN 3 for our second user group. Fast Ethernet 0/7 is placed into VLAN 9 specifically for our admin PC. By separating management traffic into VLAN 9, we isolate administrative access from regular user traffic, enhancing security and simplifying monitoring. With physical and trunking paths clear, we head back to the router to build our central DHCP server. First, we safeguard our infrastructure by excluding static addresses, blocking point 1 through point 10 across all three subnets so gateways and switch management IPs aren't accidentally leased out. This exclusion range ensures our critical network devices always keep their manually assigned addresses. Then, we build three distinct DHCP pools. VLAN 2_pool targeting 192.168.2.0/24 with default router 192.168.2.1. VLAN 3_pool targeting 192.168.3.0/24 with default router 192.168.3.1. VLAN 9_pool targeting 192.168.9.0/24 with default router 192.168.9.1. Each pool includes a DNS server option for name resolution, which we set to 8.8.8.8 for simplicity. Because each pool matches a router subinterface subnet, incoming DHCP requests on a particular subinterface automatically map to the correct pool based on the source VLAN tag. This eliminates the need for DHCP helpers or relay agents. Now for the moment of truth, testing automatic IP allocation and end-to-end routing. We open our client devices and toggle network interfaces from static to DHCP. Within seconds, we see PC1 on switch 1 poles 192.168.2.11. PC4 on switch 2 poles 192.168.3.11. The admin PC on switch 2 poles 192.168.9.11. Notice how the IP addresses fall perfectly within our excluded ranges, ensuring no conflicts with static devices. On the router, running show IP DHCP binding confirms all active leases with timestamps and MAC addresses. Finally, we run a cross VLAN ping from PC1, 192.168.2.11, to PC4, 192.168.3.11, and the admin PC, 192.168.9.11. Traffic traverses the switch trunks, hits the subinterfaces on the router, and returns successfully. The router performs the routing decision, checking its routing table and forwarding frames between VLANs. The lab is complete, and you now have a scalable Inter-VLAN routing solution.